Okay, so we're looking at single slit diffraction patterns. And here is how we think about them. When we're looking at single slits, as the name implies, we have a single slit in something. And we're going to say that this slit width here is not a little d like it was with the double slit, but it is a capital uppercase D. It's the actual like width opening of this. And just like the double slit, we are going to have some viewing screen over here somewhere. It's just a screen where the light shines. And we are going to beam into this slit right here coherent monochromatic light. And if you recall, coherent light is light that is all at the same wave pattern as it's going through, and monochromatic means it's all the same wavelength. Okay, so let's just pretend we're beaming red light through these openings here, or this opening, the singular opening as it is. So if we take a look at this opening, we may initially just think that, hey, look, if we know nothing about Huygens principle, the light will just shine through and only this section of the wall will be lit. But, you know, if you ever shown a flashlight through a wall, you know that there will be brightness through other sections. So we know that our wavelets are indeed spreading out. Okay, so we need to think about this in terms of waves and what's going on. So we know there's definitely going to be light here. The light's just going to shine through and strike it. But what happens if we go up or down our viewing screen? Well, let's pretend for a second that we're looking down here at the bottom of the viewing screen. And let's go and look at the entryway, our single slit. Now, as light is coming down, it's all traveling at approximately the same angle. Okay, our slit isn't wide enough that our angles are different here of this light. So all of this light is traveling at the exact same angle as it's coming down. And what this means is actually a very interesting thing. If this light is all traveling at the same angle coming down, we could get a kind of weird thing going on. Because if we take a look at this, maybe it's that the light from the top has to travel a slightly longer amount of distance to hit this point than the light at the bottom. And there could be some change in the path length. So this change in the path length we can find in a similar way we did with the double slit by making a triangle here. And when we make a triangle here, such that now all of this light on this side over here, this is all the same length. But that means up here, there is some extra path length that has been traveled. This is all extra. Okay? And if this is some extra path length that is traveled, if we can figure out what that path length is, we'll be able to figure out the size of it compared to something else. Now, if we take a look at what we have here, look at this capital D. This capital D, remember, is this long side of our triangle. And it appears that if we take a look at this, this angle within here is the same angle that these have deviated downwards, which means that this extra side here is equal to D sine of theta. Okay, that is some extra distance. And just like we saw with the double slit, hey, if this D sine theta happens to equal something, maybe some of these rays of light, or some of these waves of light, are going to be at perfect offsets such that we're going to have constructive or destructive interference. And if we split this slit opening in half right here, then there is the possibility that from this halfway point that we could have this d sine theta equals a whole wavelength. And at this halfway point right here, maybe the extra distance there, maybe this extra distance is like lambda over 2. Well, the reason why this matters is because if at the top in orange we have a full wavelength shift, but halfway we only have a lambda over 2, this implies that if I go down a little bit here and I go down a little bit from here, these shifts on the green are also going to be a difference of lambda over 2, just like the shift between the orange and the blue was lambda over 2. And this means that if we have an infinite number of these waves going all the way down, every wave will be canceled out with every other wave at some point, assuming that this d sine theta is some integer value of lambda. And what this means here is it kind of means the opposite of the double slit. What it means here in this case is if this extra path distance, this d sine theta, if this extra path distance is equal to an integer value of the wavelength, we're not going to get a bright fringe anymore. What we're instead going to see is darkness. We're going to get a dark fringe instead. And this is going to play with m equaling 1, 2, 3, 4, 5, ... In this same vein, then, what this means is that if this extra path distance for the full set, the d sine theta, is if d sine theta happens to equal a half wavelength shift, then that'll mean the halfway point is lambda over 4. And in doing this, we will instead see a m plus 1/2 lambda, very similar or nearly identical to the double slit, but just with a capital D. These are going to be our bright fringes. And once again, this is for m equals 1, 2, 3, 4, 5, ... Okay, so this equation here is very similar. It's almost identical to the double slit equation. D sine theta equals m lambda, d sine theta equals m plus 1/2 times lambda, but the darks and the brights have flipped, okay? And it is due to the fact that we're actually thinking about this setup in a different way. We're thinking about how this distance here of the slit width itself, as we gain some extra distance in orange, halfway down, I could constructively destructively interfere with myself through this slit. And if that happens, we're going to have a dark spot. Okay. Now, what this is also going to cause here is something a little bit weird. When we look at this actual output from a single slit, what we're going to find is, since this is a dark spot and this is a dark spot, what we're going to see for our curve, for our intensity curve, is something like this, right? It's going to look very similar to before, and maybe it'll be easier if I draw it over here. I'm a better drawer going up and down. So let's just pretend for a second that the slit is above us and the light's coming down. But what we'll see here is a, nice curve. Oh, I am struggling. Oh my goodness, we're just doing it like this. Much better. Why was that so difficult? We'll see a nice curve like this, and then the other peaks further out. But it is important for us to remember the following. This right here, these are the m lambda terms. So this first fringe here happens at, or this first dark point happens at negative lambda and at positive lambda. And then our first bright point happens at negative 3 lambda over 2 and positive 3 lambda over 2, with this being 0. At lambda over 2 and negative lambda over 2, we are still inside the central fringe. Here at negative lambda over 2 and here at positive lambda over 2, you're still inside the central fringe here. And this is different than the double slit. When we ran the double slit equation, if you recall, when we did the double slit, this being 0, this dark point was at negative lambda over 2, and this bright point was at lambda, or negative lambda. And then this is positive lambda over 2, and then this is positive lambda. Okay, so with a single slit, our central maxima, our central peak here, is actually going to be larger. It's going to be wider. It's going to be broader than the double slit. Okay, so the single slit, it has a wider central peak here than the double slit will. And that's simply because our double slit has a dark point at a half wavelength initially, and we don't see our first dark point on a single slit until a full wavelength. Okay, so that's an important thing to keep in mind in what's going on here. It is a slightly different setup, a slightly different problem. It's very important to recognize what's going on in these graphs. These graphs are very important. Hint, hint, wink, wink, blink, blink. Okay, so that's a very important thing to recognize, that this right here is not a bright point. You're still inside the central. If you want to ID your central maxima and see how large it is, you actually have to look at dark regions here. And that's what we're going to look at in our next example. Okay, so important thing to keep in mind with the double slit. This is just a derivation of it and kind of what we're looking at, how we think about it. Very similar equations, d sine theta equals m lambda, d sine theta equals m plus 1/2 lambda, but recognize that the bright and darks have flipped from the double slit and what we're looking at here. Okay, but for now, this is finished. In our next example, we're going to look at actually figuring stuff out with the central maxima for the single slit and manipulating these equations a little bit more. But until then, adios, and take it easy.